Hello and welcome to the debugging point. Today I'll be talking about introduction to pointers. So before giving you introduction to pointers, let me tell you something about pointers. Pointers are very specific to two languages, that is C and C++. You won't find this concept anywhere other than these two languages. Alright, so let's begin. First, let's discuss about this piece of code. Okay, so on line 5, it's written int I is equals to 10. So what does this mean? How will the compiler process this information, this piece of code? So what the compiler will do is that it will actually allocate 4 bytes of memory to I, and these 4 bytes of memory which are allocated to I will then, in that memory, the value 10 will be stored. So this 4 bytes of memory will have a starting address. In this example, I have taken that address to be 127DA. This is a hypothetically we have taken an address just for the sake of example. Alright. Now there is a very fine possibility that there is not only a single variable in our piece of code. There is a possibility that there are multiple such codes, multiple such variables in our code. Alright. Let's say our code also has some other variable j, which has a value which is of 4 byte. It is also an integer and has value 12 stored inside it. So now try to think, how will the compiler know, or how will the compiler remember that which part of the code which part of the memory actually represents variable I, and which part of the memory will actually represent variable j? Because there is a huge memory and there has to be some way of knowing or remembering that which part of the memory, in which part of the memory is actually I present and j present. So for that, what compiler does is that it actually maintains a table. It maintains an entry table in which it has the name of the variables. In our case, it is I and j. The type of the variable, that is, if it is an integer or a character type or a boolean type or whatever it is, and the starting address, which in our case for I is 127D8. Alright, this entry table is made by the compiler and it is made at the compile time. This is made and maintained solely by the compiler. Alright, so let's say if we are searching, if our code needs to read the value of I or simply manipulate or perform some operations on I, so what the compiler will do is that it will search through this table, this entry table, and find I. So it will know that I is of an integer type and I has an starting address of 127D8. Now the compiler knows that integer is of 4 bytes. So it will go to 127DA address and it will read 4 bytes of memory. So when it will read 4 bytes of memory starting from this starting address, which is 127DA, it will actually get the value 10 and it will return the value of 10, and then whatever operations are to be performed will be performed. So this is how the values are physically present in the memory and they are taken out from the memory. This entry table which we were referring to so far, this entry table is actually known as symbol table. This entry table is known as symbol table. Alright, so let's write some code about it. Just a second. Just a second, sorry for the inconvenience caused. Alright, so the concept, see this, I hope the concept of symbol table is clear to you. Now moving on, the address of a variable actually can be checked through an ampersand operator. See, every variable has a starting address, alright, associated with it, and it can be checked or it can be obtained using ampersand operator. This AND symbol is known as ampersand operator in C++. So what this ampersand operator does is that this ampersand operator is used to find the address of the variables. Now let me show you how. See, as soon as I run this code, you will see the value cout10 is printed for value I, and ampersand I actually prints the address, this 06CDFEEC. This is the address of variable I in which it is present. Now how this code would have been processed? See, first the compiler, first we had int cout I. So for that the compiler would have searched through the symbol table for variable I. It would have got the address of variable I. It would have gone to that address in the memory and read 4 bytes of memory, because it knows that an integer takes 4 bytes of memory. Alright. Then it would have, then for the ampersand part, when we had executed, when the compiler has to execute this statement cout ampersand I, then what it would do, it would actually again search through the symbol table and check for I. When it finds I, it simply prints this address of the variable instead of fetching the value by going to that address. Alright, so it simply just prints the address. Now we saw that the address was in some 0x6defeec, some this format. So what this format actually is, let's discuss about it. So the 0x in the starting of the address, let me re-execute the code for you. 0x6fd6defeec. So what this means, 0x actually means that the digits, the number written after it is a hexadecimal number. Now what's a hexadecimal number? Basically, see, decimal numbers are numbers with base 10. So basically you have numbers ranging from 0 to 9. Similarly, in binary you have a base 2, so the numbers are 0, 1. Likewise, in hexadecimal numbers, the base is of 16. So you have numbers ranging from 0 to 15. So the numbers from 0 to 9 are written as it is. However, 10 is not written as it is written as A. Similarly, for 11 we write B. For 12 we write C. For 13 we write D. For 14 E, and 15 for 15 we write F. Alright. So this is it for the hexadecimal numbers. So basically addresses in C++ are in hexadecimal format. Alright. Now moving on, we have a concept called pointers. So let's discuss what pointers really are. Pointers are the variables that store the address of other variables. See, for storing integers, we have int data type. For storing characters, we have char data type. Likewise, for storing addresses, we have a special data type, a special basically variable type, which is known as pointers. Pointers is a category of variables which do not store the value, rather it stores the address of some other variables. Alright, so there has to be a legit method to define pointers. Unfortunately, pointers p equals to ampersand I. Now we know that ampersand is actually the address of operators, but pointers p equals ampersand I is not a good method to define pointers. It is not rather a legal method to define pointers. Define pointers, what we do is int star p is equals to ampersand I. Int star means it is a pointer to an integer which has a name p and it has the address of variable I stored in it. Alright, so if we can actually print this statement in our code. So let's try to print this here. So this second line, actually the value of p and ampersand I comes out to be same, because the value of ampersand I is actually stored inside the value of p, and p is nothing but a pointer, so it stores the address of other variables. Alright, so this concept of pointers is not only restricted to int data type, rather it can be valid for any data type, which means that we can have this concept for character, for float, for boolean, for double, or any other kind of data type. The concept remains the same. Alright, let me explain it to you with diagrammatic representation here. So what actually happens when we write this line of code? This line of code is that, see, first we had I, alright, a 4 bytes of memory was allocated to it, an entry in the symbol table was made corresponding to I, and then the value 10 was stored inside this physical memory. Alright, likewise, when the compiler encounters this line of code, line number 11, int star p is equals to ampersand I, what it does is it allocates 8 bytes of memory to the variable p, and then it makes a entry in the symbol table for the variable p. That variable p is an int star type variable, and it is located at the address 6C13B. Alright, and then it stores the value of address of I inside this variable. Alright, this is how things are going. So this is how basically a pointer is initialized, and the value is stored inside a pointer. You might have noticed by now that the basic concept, the underlying concept of any ordinary variable that we have studied so far and pointers is absolutely the same. Alright, now how do we dereference values from a pointer? Now see, you might have realized by now that there can be basically two methods to get to the value of I. First is the conventional method which we have been using so far, which is through I, right? We can see out I and we directly get the value 10. And we also know the method how it's done using symbol table. But since P has the address of I, so through this address also we can reach to this memory and read the value 10. Alright, but how is it done? This is done basically using the dereference operator. Alright, so let me tell you what dereference operator is. This star which you are seeing on the screen, star, is actually known as dereference operator. So when you execute star P statement, what essentially happens is that star, you go to the address of the variable and you dereference the value on that address. What it means is when you execute star P, what happens? P has the address 127DA, which is the address of the variable I. Alright. So P has the address of I. So what star P does is that star P goes to that address and fetches the value whatever is present on in that memory location. You can think of star and P to be opposite in sense. I'll elaborate it further. First, let's see the execution of this code. You see the last two lines. I is 10 and star I is 10 as well. We have seen the 31st line of code earlier as well, which is ampersand I and P are essentially the same thing because P has the value of address of I. Alright. And the 30th line of code, in this line of code we have cout I, and then we have executed cout of star P. Star P, that is dereference operator on pointer P. So what it does is that P has the address of I, so it goes to star P, actually goes to that address and fetches the value stored inside I and displays. That's all it is doing. Alright. Let me further explain it to you through step-by-step method. This is a complicated procedure and you might be thinking that I am repeating steps over and over again, but it is actually very, very important. So let's see once more. See, we have this piece of code. Alright. So what we have to do with this piece of code is int I is equals to 10 and int star P is equals to ampersand I. So what will happen is a memory of 4 bytes will be allocated to I, and then this the allocated 4 bytes, an entry would be made for those allocated 4 bytes in the symbol table for the variable I. Alright. And after making the entry in the symbol table, value 10 would be stored in that allocated memory. Alright, so this would happen only for line number 6. Now coming on to for line number 7, what will happen? A memory of 8 bytes would be allocated for variable P. Alright, an entry would be made in the entry symbol table for this variable P, and then the address of I would be stored inside this variable P. Alright. Thus pointers are essentially not a different entity. Alright. They are just like variables, but they store the address of variables instead. I hope this concept is clear to you. Moving on, let us execute some code. Alright, so you must have understood by now that P and I, P star and star P, that is dereference operator P and I, are pointing to the same piece of memory. Alright, they are not different memories. So if I execute, I increment the value I, what happens is that uh, if I see out I and I see out P star, exactly same thing, both the values would have been incremented by 1 here. See, earlier both the I and the value of P were 10, but let me re-execute the code for you. Earlier both the values were 10, but when we increment I, both star P and I gets incremented. Now why is this happening? This is because P and I, star P and I actually are the same memory location. Cout I and cout star P are a result of the same piece of memory. So if I have incremented I, the star P value gets incremented automatically. The changes made through one method, through one way, would also be reflected through the other way. So here, if int j is equals to I is done, so a separate copy, a separate memory is allocated to j, in which the value of I is copied, and then that value of j is incremented. Thus, j and I are two different entities, and incrementing j does not really affect I. We can see it here with the help of a diagram. See, here I was present in the memory, j was created, it was allocated a separate memory, so a copy of I was created, the value of I was stored to the value of j. So now on incrementing j, the basically on incrementing j, the value of I remains absolutely unaffected. Alright, it does not affect the value of I, whatever is or whatever operation is performed on j. I hope it is clear to you. Now, small things. See, all the operations on P can be, star P can be performed as that we perform on I. That is, we can perform star P plus plus, star P minus minus, so on and so forth, operations like these on P, and it will actually be performed on the value I. What I mean is that, see, star P is nothing but this very piece of memory is I as well as star P. So on performing any operation, any arithmetic operation like star P plus plus or star P minus minus or star P or star P equals to like this, star P plus plus or star P minus minus or star P, or we just simply override the value of star P by, let's say we make it 100. So the value of I and so the value inside this memory will be affected. On doing star P plus plus, it gets incrementing. On doing star P equals to 100, it gets overwritten. And this can be seen through cout I as well as cout star P. Alright, this can be seen through cout I as well as cout star P. Here, let me do it for you. So if we run this code, see, both the values become 100, and on incrementing both of them result 12. I hope the concept is clear to you. Now moving ahead, can we do this thing? Is this thing legal? You tell me. Int star p is equals to int star q is equals to p. Alright, if we do this thing, what happens is that how the compiler will compile this is that a new memory of 8 bytes would be allocated for the variable q. Inside these 8 bytes, a copy would be created. The value, whatever is stored inside P, will be stored inside Q. Alright, first 8 bytes of memory would be allocated, then entry in the symbol table would be made that Q is an int star and it has so and so, it is on so and so address. Then the value of P would be copied into the value of Q. Alright, so now Q also has the address, is also a pointer and also has the address of variable I. So P, like P, Q also becomes a pointer to the variable I. So now whatever operations we were doing with star P, the same operations with star Q could also be done. So star P, star Q and I, all of them actually represent the same piece of memory, and through any of these, if we perform any operation over any of these, let's say star p plus plus or star q plus plus or I plus plus, then the same piece of memory will get manipulated and the effect could be seen through any other method also. Like if we do star p plus plus, then star p, if we do star p, star q or cout I, then all of them will display absolutely the same result. Alright, a few warnings that I would like to give you before ending this session is that, see, if you have int I, we do cout I, we do I plus plus, and then we are doing cout I. So what essentially is happening here is that if I compile this piece of code, then I will be having some garbage value. So we are printing that garbage value and we are incrementing that garbage value. Absolutely not a problem. Alright. But what if we do something like this? Int star p, we define a variable, we define a pointer, and that pointer is not initialized with anything. So if we do cout p, what happens is that a garbage address gets printed. Alright, see this address, we have not allocated this address to P. So there will be some garbage value, some garbage address present in P by default. Now, what if we perform some absolutely some arithmetic operation on this star P? See, P is a garbage value, so P has a garbage address, so it is technically pointing to some garbage memory space. Alright, so performing operations on star P can lead to very, very, very fatal results because you don't know what really is kept on that address. You really do not know. So there is a possibility that there is some important information of your operating system kept on that memory space, or that memory space is not, you are not allowed to access that memory space, or you might overwrite that memory with some other value and your system may crash. So it can lead to very fatal results. So a piece of suggestion to you, that never ever even define a pointer with, never ever keep it non-initialized. Always initialize it with some variable. If you do not have any variable, then either define it with null. Null means that it is not pointing anywhere. Alright, so this is a safe thing. If you do not have any memory address, any memory address right now, so initialize it with null rather. You can initialize null or make it 0. 0 is also null, or put null pointer to it. All these are the same things. Null pointer, null or 0. All these make the value stored inside P0. So basically, see, all these make the value stored inside P0. So basically, you are not pointing anywhere right now. Alright. I hope this session was helpful to you. Thank you for watching.